Hello and welcome to my video on polynomial functions of higher degree. This is the second section of Chapter 2. Our skill objectives for this video are 1. Determine end behavior of a polynomial. We've already done that in class, but this will be a review, very quick review of it. Number 2, identify real zeros of a polynomial function and what's called their multiplicities. The third thing is to sketch a polynomial using intercepts and end behavior. The conceptual objectives: understand zeros correspond to x-intercepts and understand the intermediate value theorem. Very quickly, just want to review the end behavior that we talked about in class and also review the idea of the general polynomial that we talked about last time as well in the last video. Remember the general polynomial of degree n. In other words, it's f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus plus a sub 2 x squared plus a sub 1 x to the first plus a sub 0. That is that alphabet soup definition of a polynomial. The thing we want to remember with this, though, is number 1, n must be an integer. Okay, n must be a positive integer. And the other thing is the coefficients must be real numbers. They can be square roots of 5. They could be 1/2. They could be weird fractions, any other weird fraction. But they have to be a real number, something that shows up on the number line. And what we have with end behavior, when we talk about end behavior, we're talking about what happens to the polynomial as x gets very large, very far from 0, in both the left and the right direction. And really what happens with it is that in any polynomial, there's one term that takes dominance as x gets very far from 0. And that term is this highest degree term, a sub n x to the n. And so what we know is that any polynomial f of x is going to have the same behavior as the power function a sub n x to the n. Basically its highest degree term by itself, that power function. Here's a table very similar to what we drew last time. It does add on a little bit of information on here. First up, what you want to notice is across the top in white is what we're looking at when we deal with x to the n, and where the exponent n, when n is even and when n is odd, the behavior that will be exhibited. And over on the left side, you'll notice that a sub n is, in this first one, is a sub n is greater than 0, so it's positive. And in the second one, a sub n is negative. So what we're looking at here, this first piece right here, is going to tell me the behavior when I know that the leading coefficient, a sub n, is positive and the degree of the term is some even integer. So what we have in that case is that as x goes off to either positive or negative infinity, the y values are going off to infinity. In other words, that polynomial, if it's an even degree where the leading coefficient is positive, eventually that polynomial, both sides, are going to be going up. As I go off to the left, it's going to end up going up. Say I'll go off to the right, it's going to end up going up as well. What's going on, again, as I talked about in class, what's going on in the middle when you're close to 0, it could be moving all over the place. But eventually, this is the behavior that it will exhibit if it's an even degree and a sub n is greater than 0, is positive. If it's an even degree and a sub n is negative, no surprise, because we know that when we have a negative like that, it's going to reflect it over the x-axis. So in this case, everything as x goes off to positive or negative infinity, y is going to be going down, going towards negative infinity. So eventually, both ends are going to be going down. Then we get over here to the far right where n is odd. Okay, so in this case, now we're looking at cubics, 5th degree. And what happens there is that when a sub n is greater than 0, it's going to go, on the left, it's going to go down. So as x goes to negative infinity, y is also going towards negative infinity. And as x goes towards positive infinity, y is going to go positive infinity as well. So eventually, as you go off further to the right, it's going to be going up. And again, the exact opposite is true when a sub n is less than 0. As x goes to negative infinity, y is going to be going up to positive infinity. And as x goes off towards positive infinity, my y values are going towards negative infinity. So this is a chart that we have, and we'll be looking at that and using that to determine end behavior, especially once we start looking at making graphs, sketching these polynomials. Next thing we have is real zeros. Now, when we talk about zeros, there's four different interpretations you need to be familiar with. Okay, so we're going to let, in this case, f of x is a polynomial function, and a is a real number, some real number, and then the following statements are equivalent. You must know that these four and be able to interchange them. Number one, x equals a is a solution or root of f of x equals 0. Number two, the point a0 is an x-intercept of the graph of f of x. So if you know that x equals a is a solution to f of x equals 0, you know that graphically it will also be the x-intercept for the graph of f. X equals a is a 0 of f of x. Well, that should be pretty familiar just because of the fact that a lot of times when you hear 0 and root, they actually get interchanged. Here's another one, though, and this is another important one. X minus a is a factor of f of x. One of the things we're going to be doing is we're going to be asking you to identify, to find a polynomial when you're told these are the zeros that you have in the problem. So in that case, we want to use the fact that if you know a number is a 0, then x minus that number will be a factor. Next, we have multiplicities. Now, multiplicities, really it's a way of looking at how many times a particular number occurs as a 0, okay? Or how many factors of x minus a that polynomial has. In this case, multiplicity of a 0, if x minus a raised to the n power is a factor of f of x, then a is called a 0 of multiplicity n of f. Let's look at a couple of examples here. In the first one, what I have is one of our factors, if you will, is x minus 2 to the third power. In this case, we know 2 is a 0, and because there's the exponent of 3, we know it has a multiplicity of 3. In this case here, we have another polynomial. It's actually in its factored form. It's x plus 1 to the second power times x minus 4 to the third. So in this case, negative 1 is a 0 of multiplicity 2, and 4 is a 0 of multiplicity 3. Why worry about multiplicity? Well, multiplicity, the multiplicity of a 0 actually is going to have an effect on how the graph of a polynomial looks. Okay. First up, if we know a is a 0 of f of x, then it's going to have a multiplicity. It could be a multiplicity of 1. It could be higher than 1. Okay. If that multiplicity is even, what that means is that at that value, the polynomial graphically is going to come, it's going to touch the x-axis at the point a comma 0, and then it's going to change direction. Okay, so the function actually does not cross the x-axis. To both sides of, just to the left and just to the right of a on the x-axis, the function values are going to have the same sign, either both positive or both negative. But what in essence happens is that the graph touches the x-axis and then turns around. Okay, and it touches it at that point a comma 0. If the multiplicity of a 0 is odd, then what's going to happen is that to one side, when I pick values of x just to one side of a, it might be positive, and then to the other side it's negative. Or it could go the other way. It could be negative and then positive. But the end result is that when you have an odd multiplicity, I know that the graph of the polynomial is going to cross at the point a0. It's going to actually cross the x-axis. So I can use those to help me out. So if I have a polynomial, I'm trying to sketch a polynomial, I know the multiplicity of one of the zeros is 2. I know it's just going to touch it. It's going to touch the x-axis there and then go back up. Whereas if I know it's 3, I know it will end up crossing the x-axis. One of the things that we have to do in order to find the zeros, really what that means is that we are going to be factoring. So the example we have right now is f of x is 2x to the fourth plus 5x cubed minus 3x squared. Now, what I'm looking at doing with that is I need to go and factor this. So I start out here with our polynomial, and we want to go through and set it equal to 0 because we're looking for zeros, so we need this polynomial to equal 0. The first thing I noticed when I looked at this polynomial is that I do have a common factor of x squared that I could pull out. And so I pull out the x squared, and I'm left with the quantity 2x squared plus 5x minus 3. So now it's factored to this point. The next step I have to do is factor the remaining polynomial, that 2x squared plus 5x minus 3. So what I'd like you to do right now is I'd like you to pause the video, see if you can figure out how 2x squared plus 5x minus 3, how that quadratic actually factors. So pause the video, and then we'll come back to this and finish this problem up once you're done. Welcome back. Well, in this case, when I factored that, the 2x squared plus 5x minus 3, what I got is that was 2x minus 1 times x plus 3. And so my polynomial f of x of 2x to the fourth plus 5x cubed plus minus 3x squared has a complete factorization of x squared times the quantity of 2x minus 1 times x plus 3. At this point now, since it's factored, we can now identify the zeros. So in this first one, we have x squared. Well, if I let x squared equal 0, the one zero I find out is that x equals 0 is actually one of those values. And it does have a multiplicity of 2. The other two zeros are, in this first one, if I let 2x minus 1 equals 0, and I solve that, I'm going to get 1/2. And in the third one, if I let x plus 3 equal 0 and solve it, I get -3. So my zeros in this case are the number 0 twice. It's going to cross, so graphically this is going to go and it's going to contain the origin, and 1/2 and -3. Now let's say we're going to go and we want to actually end up graphing this. And we want to get a reasonable sketch. When I ask you to go and make a sketch based on analysis of these functions, I'm asking you to go through, identify the important points, identify the zeros, identify the end behavior. Give me something that it would be reasonable to say that that's pretty close to the graph of the polynomial we're looking at. So in this case, we've already identified the zeros. Next thing we want to do is we want to identify the end behavior. Well, in this case, I know that the end behavior is always going to be that leading coefficient, the leading term here, highest degree term. So in this case, the degree of that highest degree term is 4. So I know graphically the end behavior as I go off to positive or negative infinity, either both sides are going to go up or both sides are going down. So, and since in this case, since it's the coefficient on x to the fourth is a positive number, what I know in this case is that as x goes to positive or negative infinity, I know my y values are going to go towards positive infinity. So I know in this case, in both directions, we're going to be going up. Now, after that, now that we know those, we know the zeros, we know the end behavior, I can go through and get a sketch of this polynomial. What we're going to do is I just added a grid, quick little graph that I'm going to use to give myself a sketch of this polynomial. The first thing I'm going to do on this is I'm going to put dots every place where we know it crosses the x-axis. So I know this crosses the x-axis, or where it has zeros. I know it has a 0 at the origin, so I put a dot there. I know it has one at -3, so I'm going to put a dot out there. And it has one at 1/2, so right here. The other thing I know in this case is that by the end behavior, as we get far away from 0, both sides are going to be going up. The function values are going to be going up. So what I know from that is at these zeros, I know it's going to be a smooth curve, and at this zero, after this zero here at 1/2, I know this curve is going to go up like that. And also after the zero at -3, it's also going to be going up. The other thing I know in this case is that at 0, it has a multiplicity of 2. So I know what's going to happen there is it's just going to touch the origin, and then it's going to change direction. Well, in this case, based on where we're at, since it had to cross at -3, I know that everywhere from -3 all the way to 0, and then from 0 to 1/2, I know we're going to be looking at values that are below the x-axis. And so my graph is going to look something along this line. It's going to come down, continue down. I'm going to change directions, come back up. It's going to hit at that origin, change directions again, and then go right through the 1/2. Now, the question that a lot of people have is this: how do I know how far down I need to go on each of these? The actual answer on this one is I do have the equation up here, and I could calculate those values, see how far down I went. But graphically, for what I'm looking for with this is I want that basic behavior, so you recognize what that's going to look like. Notice I really didn't even talk about the scaling at all. Now you might have assumed that those were 1s, but those could be each line on the y-axis could represent 5, it could represent 10, whatever I want it to be. Okay, the x values though clearly go through and are scaled to be 1 unit, because I called this one out here at -3, and that's at +1/2, so that would imply that that's 1. So there's a rough graph of this particular polynomial. Other issues that you might have, and it wasn't something we had to worry about with this one, is that if there was a y-intercept other than 0, we would have to identify that as well. Now let's look at the other direction. This time we're going to be given the zeros, and we want to find a polynomial that will match that. Okay. Now, first up, what you have to remember on this is there are an infinite number of polynomials that will match this particular set of zeros, because I can change that leading coefficient. I can use whatever value I want. For our purposes, when I do these, I will generally let that leading coefficient be a 1, so I won't even worry about that, about using any other values there. Now, in this case too, on this problem, we know that -4 is a 0 and it has a multiplicity of 2. That means it occurs twice. And so remember what we said is that if you know a number is a 0, then x minus that number is a factor. Well, in this case, I know -4 is a 0, so x minus -4, x plus 4 would be a factor. The fact that it has a multiplicity of 2 also tells me that this should be a squared on that it should be one of the factors of our polynomial would be x plus 4, that quantity squared. Then we know that 1 is a 0, so that tells me x minus 1 is a factor. And we know that 3 is a 0, so x minus 3 will be a factor. At this point, our job is going to be to find the actual equation of this polynomial. Well, to do that, what I have to do is use the fact that I know that these are factors of that polynomial. And so I know that if I take the product of those, in other words, I take x plus 4, that quantity squared, times x minus 1, times x minus 3, that is actually equal to f of x, our polynomial. And so what I'm going to have to do now is multiply that out. So pause the video. I want you to go first multiply out the x plus 4 squared, and the next thing I'd like you to do is multiply out the x minus 1 times x minus 3. See what you get. So pause the video, do that, and when you come back, we'll have that answer there, and then we'll talk about how we finish up that problem. Okay, in this case, welcome back. In this case, when I went through and did the product of x plus 4 times x plus 4, you should have come up with x squared plus 8x plus 16. And when I multiplied x minus 2 times x minus 3, you should come up with x squared minus 4x plus 3. Remember, you do have to FOIL all of this. Now, what we have to do is we want to finish this problem up. I need to multiply these two pieces out. And what I'm going to do is, in essence, it really kind of expand that FOIL. I'm going to go through and I'm going to take the x squared and I'm going to multiply it by everything I see in red. And then I'm going to come back, I'll multiply the 8x by everything I see in red. Then I'm going to multiply the 16 by everything I see in red. At that point, once I have everything multiplied out, I can then begin to combine like terms. So what I'd like you to do is pause the video and write out what you get when you take x squared times all of this, and then do the 8x times all of that, and then the 16 times all of that. When I went through and multiplied that out, what I ended up with is I took the x squared times all of this. I got x to the fourth minus 4x cubed plus 3x squared, plus the 8x times all of that gave me plus 8x cubed minus 32x squared plus 24x. And then when I took the 16 times all the stuff in red, I got plus 16x squared minus 64x plus 48. At this point, what we need to do to finish this problem up is I need to just go and combine the like terms. So in this case, I have f of x equals, well, in this case, I just have one x to the fourth term, so it's x to the fourth. I have a minus 4x cubed plus 8x cubed. Those are the only x cubed terms, so that is going to end up being plus 4x cubed. Now with the x squareds, I have plus 3x squared minus 32x squared plus 16x squared. So when I take the 3 minus 32 plus 16, I'm going to come up with a negative 13 x squared. And now I have my 24x minus 64x, so it's going to be minus 40x, and then plus 48. So there, this is one polynomial that has 4 zeros, where negative 4 is a 0 with a multiplicity of 2. 1 and 3 are also zeros. So I get this polynomial right there as having the answer to this problem. Now again, I could go through and I could take this whole thing, multiply it by whatever number I want, and I would generate another polynomial that would have those zeros. Another thing we're going to be asking you to do is to identify different information about the polynomial. In this case, the couple things that you have to realize on this, you're going to have to identify the zeros, what zeros they have, and what multiplicity they appear to have. And you just want to use the smallest multiplicity, I guess, that you could have. You want to do the degree of the polynomial. You want to identify if the leading coefficient is positive or negative, and you want to identify the y-intercept. So let's start out with this problem here. In this case, I know I have it marked off in my grid that that's negative 5 over there. This is positive 5, that's positive 5, and this one is negative 5 there. So I know that the scale on the x-axis and the y-axis happen to be 1. Because of that, I know right here that this function crosses the x-axis at negative 2. So one of my zeros in this case is going to be negative 2. And I'm going to say because that has, it just crosses there, that has a multiplicity of 1. Another zero I have is right here at positive 1. And again, it crosses, so I'm going to say at positive 1, it has a multiplicity of 1 as well. So positive 1 and its multiplicity is 1. The next spot that I have is right here, and in this case I know it touches. The graph touches at positive 4. And so because it touches and then changes direction, I know it's going to have an even multiplicity. So I know it has a multiplicity of, at positive 4, it's going to have a multiplicity of an even number, and generally you're going to want to use the smallest one that we could have, so in this case it's going to be 2. So for these particular problems, what I know is that negative 2 has a multiplicity of 1, so I'll put the multiplicities in red. 1 has a multiplicity of 1, and I'm going to say 4 has a multiplicity of 2. And now we have to identify the degree. Well, here's the cool thing. The degree of the polynomial, you just add up those multiplicities of its zeros. So in this case, the smallest degree polynomial I could be looking at here would be a 4th degree polynomial. So I would say, in this case, n is equal to 4. Now, now we have to look at the leading coefficient. Is this thing, is the leading coefficient a positive number or negative number? Well, that goes back to our end behavior. We know that it's an even degree, so I know both sides are going to go up or both sides are going to go down. Since this goes down, I know that when it went down, the leading coefficient, a sub n, was negative. So in this case, since both sides here do go down, I know that a sub n in this case is less than 0. It's going to be a negative number. And the last thing I need to identify is the y-intercept. Well, the y-intercept, I can see that. It's right there. And I know that y-intercept is actually equal to, is at the point 0, 1. The last thing we're going to look at today is what's called the intermediate value theorem. And again, this is what's called an existence theorem. It tells you something occurs, but it doesn't tell you exactly where. It gives you a general location, but it doesn't tell you the specific value of x where it's going to happen. In this case, what we're going to do is we're going to let a and b be real numbers such that a is less than b. That's just arbitrary because we don't want the two to be equal. So we're going to say that a is less than b so that one is smaller and the other is bigger. And we're going to let f of x be a polynomial function. Now, the nice thing about a polynomial function is the domain is all real numbers. So I know that when that there is a value that I can plug a in for x into this polynomial, and I can plug b in for x and get function values. So if f of a and f of b have opposite signs, in other words, if one is positive and the other is negative, then because it's a polynomial, then I know there is at least 1 0 between a and b. So in other words, if I just know that, let's say f of a was positive, f of b is negative, I know somewhere between a and b that polynomial has to cross the x-axis. So let's look at an example here. What we use this for is to identify a general location of where we might actually have a 0. In this case, I have f of x equals x squared plus 5x minus 4. If I go and find f of 0, well, f of 0 is equal to 0 squared plus 5 times 0 minus 4. I get negative 4. And if I find f of 1, I get 1 squared plus 5 times 1 minus 4. And the result there is going to be positive 2. So because by the intermediate value theorem, I know that somewhere between 0 and 1, my function crosses the x-axis, or there is some value. There's going to be some value between 0 and 1 here that I know that if I plug that into function f, I'm going to get 0. That's what the intermediate value theorem tells us. It tells us it happens. We don't know specifically where it's at. We just know that it definitely must occur. This now concludes my video on the polynomials of higher degree. In class, we'll talk a little bit more. Make sure if you have any questions that you get those written down. And in class, we'll talk a little bit more about all this material, especially the intermediate value theorem, what it means, what it's saying. And we'll look at a couple examples in terms of sketching, how we go through and sketch a polynomial based on finding the zeros, finding the intercepts, and looking at the end behaviors. So we'll look at a couple examples there. And we're also going to look at one more example where I give you zeros of a polynomial, and then we're going to be asked to find the a polynomial that has those zeros. Now the zeros we used were all integers. Well, we're going to look at some that are not integers. So that's what we're going to look at in class as well. So hope you have a good evening, and we will see you at our next class.